All right, colored pens up. Let's see how we did with solving a linear system. What is the solution? Quiet students, stay on your toes today. You will be called on randomly out of the blue, and you need to be prepared. Start with Davis, Dalton, Nathaniel, and then Sebastian C.
X equals negative 6.67.
Okay?
Negative 6 and 2/3.
Okay?
X is equal to negative 6 and 2/3.
Okay? Okay? Well, the correct solution is 16, 17. So first, issue number 1. Very few students in my class even knew what a solution to a system looked like. Yet, we spent an entire chapter on solving linear systems. Does anyone remember what chapter it was? John? Yeah, well, that's a section. It was chapter 7, yeah. Solving linear systems. In fact, you know 3 different methods for solving a linear system. Now, I don't blame you for not remembering. It's been a while. But please understand that in 3 weeks, not only will you have to know exactly what to do, you will have to be an expert at this. So, you need to pay attention. Solving a linear system means we are trying to find an ordered pair that makes the system true. Anything coming back to you now? Any methods possibly that are coming back to you? Plug in a 0 for each. That will get you the intercepts of one equation. So you're remembering something from the past, that's good, but you're remembering something from something totally different. Michaela? Slope-intercept form could help, maybe. Kenya? What is it? Substitution, that's one method. What's another one, Janae? Elimination, that's the other method. What's the third method? Nathaniel? Sort of related, but we've got substitution, we got elimination. There was a third method. It was actually the first one you learned. Chris? Not extrapolation. That's something totally different. Graphing. So, this is perfect for elimination. Elimination means we need both equations set up in the same format. So we need to rewrite this equation so that it's in standard form. Everyone's got their colored pen ready. This is where you learn and refresh. So to get it in standard form, we need the 3x to go to the other side, which means we subtract it from both sides, and we end up with this. Now we need the second equation in standard form so that all the terms line up. So we need the x term to jump to the left, and we need the 12 to jump to the right. So we'll subtract 5x from both sides, and that will jump to the left, plus 4y. And then we need the 12 to jump to the other side. We subtract it, and we end up with this. So now we have all the terms lined up, but now we need to look for something. What is it that we're looking for when we use the elimination technique? Kenya? That's right. So are there opposites in any of the columns? Is there opposite here, and is there opposite here? No. So we have to make opposites. What could we do to make opposites? What could we do to make opposites? Sebastian R. Times each of them by -1? Well, if we time... Ah, very good. You caught your mistake. Yeah, multiply one of them by -1. If we multiply both of them by -1, then we're going to end up back where we started. Multiply this by -1, and then that sign will flip, that sign will flip, and that sign will flip. And now we have opposites, just like Danielle said we needed to get. And we add down. 3x and -5x is -2x. -4y and +4y will cancel out. Equals -32. You can easily see, divide both sides by -2, x equals 16. How do we get the y value? How do we get the 17? Matthew?
Put in 16
Yeah, plug the 16 back into one of these and solve. The first equation is set up pretty nicely for this. 4y equals 3 times 16 plus 20. 16 times 3 is 48. Plus 20 is 68. So we get 4y equals 68. Y equals 17. The ordered pair that makes this system true is 16, 17. And again, that is called elimination. Comments, questions, concerns? Issues, problems? John?
If you were to do it the old way, it would still work out. Right?
Yep. Although it would be a bit of a pain, especially now seeing the answer is 16, 17, your graph would probably be huge. So graph and check would work, of course, and substitution would work. But substitution would be ugly because you would have to isolate one of the variables and you'd end up with fractions. For example, if you isolate the y, you end up with 3/4 x plus 5. And then you have to deal with that 3/4, and that makes an uncomfortable situation later on. Elimination is very often the easiest method, although substitution, depending on the situation, can be very easy as well. Daniela, yes. How did we what? How did I get from here to here? Well, how do we get this 3x to jump to this side? I'm sorry? You could if I subtract 4y from both sides, but then I end up with a 0 on the left. And I end up with everything else on the right. So I was just trying to get the x to come over here so that I had the x and y on the same side. Standard form of a linear equation. X and y need to be on the same side. You could put everything on the right. That's fine. It makes you more comfortable if the x and y is on the right side? Okay. Any other comments, questions? Okay. We are starting chapter 11. Hopefully you noticed that we are skipping 11.1. And today we start learning about radicals. Radicals, square roots, same thing. And we're going to start with expressions that have radicals in them. And we're going to learn how to simplify a radical expression. You have 3 conditions. 3 things have to be true for a radical expression to be simplified. There can be no perfect square factors inside the radical. There can be no fractions inside the radical. And there can be no radicals in the denominator of a fraction. Remember, these are notes, so you need to skip over unimportant words and use shorthand and abbreviations for things like fraction and denominator and radical. So, these criteria, these conditions, we're copying down to fall back on later on. You're going to see why we need this written down. These are reminders of what has to be true, especially the no perfect square factors and no radicals in the denominator. Let's take a moment to finish that, and then I'm going to introduce you to what I'm talking about. So whether you're done copying or not, I want you to pause. And here's an example of what we're talking about. We start on the left-hand side. Here's the original expression. Radical 12x to the third power. That's an expression. It's algebraic, and it has a radical. So this is what we're going to learn how to simplify. I don't want you to copy this down. I just want you to look. This can be rewritten into a multiplication problem, the product of factors. 12 can be split into 4 and 3. X to the third can be split into x squared and x. The reason that these factors are important is because 2 of them are perfect squares. 4 is a perfect square, and x squared is a perfect square. And when you take the square root of a perfect square, it comes out to a whole number. When you take the square root of an algebraic expression that's squared, you get the root of it, which is the x. And so here's what we end up with. This is simplified form of this. And this is what you're going to learn how to do today. You read this as 2x radical 3x. That's how you read that. There are no perfect square factors inside the radical. There are no fractions in the radical. And there's no radicals in the denominator. There is no denominator in this one. Yes, Chris? Just hold on to your question. You're going to see tons of different examples of things. See if I answer your question in the next 10 minutes. And if I don't, ask again. If you need to jot down a little question for yourself, go ahead. But I'm pretty sure that I'm going to answer your question. All right? Now, this last condition, there can be no radicals in the denominator, presents a particular challenge. And we're going to learn a technique to solve that problem. The technique is called rationalizing the denominator. Rationalizing the denominator is a process for eliminating the radical. And it's actually a very simple process. It's based on something that you've known for a couple of years already. So, again, I'm going to start all the way here on the left. We have another algebraic expression with a radical in it. 7 over radical 2x. Radical 2x is in simplest form. There's nothing that you can do with that. However, it's in the denominator. We're not allowed to have a radical in the denominator, so we have to do something to get rid of it. And it's very simple. You multiply the whole fraction by 1. This is actually equal to 1. Anything over itself is equal to 1. When you multiply a fraction times 1, you're not changing its value. But we are doing something creative. We're taking this expression and multiplying the whole fraction by it. And so what happens when I multiply a radical times itself, you're going to learn over the course of today, is that the expression jumps out of the radical. A radical times itself leaves us with the expression inside the radical. And then you just multiply the top and you get 7 radical 2x. So this is simplified form of this. I don't want you to copy that down. We're not ready to yet. I'm just introducing the idea to you. You probably don't understand what I'm talking about yet. You're not supposed to. We have quite a bit of building to get to the point where you're going to understand. The process is going to take a long time. Your hand's going to get tired, your brain's going to be pushed. Okay, so I'm just giving you a heads up about that. You're going to be pulling ideas from different parts of the year. You're going to be pulling ideas from different parts of the year. You're going to have to be able to put them all together. It's going to take a lot of brain power, and as I said, the building process is a bit long. So sometimes I start you guys off with the most difficult question, and then we go to the easier ones. That works sometimes. That won't work today. It won't make any sense. So we're going to start building. I have to start by going back to this. What is a perfect square and what is a square root? We're going to explore this in a particular way. Don't draw all the squares. Just draw one of them. Draw it big enough to write something inside of it. A number or a letter. So the question is, what is a perfect square? And then the second question is, what is a square root? We're going to answer both of them at the same time. So could I have a volunteer give me an example of a perfect square? Give me a perfect square. We've got a lot of people who know. Excellent. 16. Great example. So if everyone will write a 16 inside your first square. Now someone explain why 16 is called a perfect square. Why is it called a perfect square? Could you?
Because the number times itself equals 100.
Okay, so what is the number in this case?
4.
4. So 4 times 4 gives us a 16. And so that's called a perfect square because it forms a perfect square. That's what a perfect square is. Now, can someone tell us, just by looking at this picture, what a square root is? Think of the phrase, square root. What is a square root? John? 16 is what? The square root of it is 4. So the number inside the square is a perfect square. The number outside the square is the square root. Can I have another example of a perfect square, please? Please. 4. So 4 is a perfect square. What number do I put on the outside of the square to finish the picture? Caleb? 2. So 4 is a perfect square because we can multiply a number times itself and it forms the 4. And then the square root of 4 is 2. Chris, you had a comment or question, or you're going to give me another one? Go for it. 676. Good. I don't have that one memorized. What number times itself gives us 676? 26. Great. So 26 times 26 gives us 676. I'm trusting him because I need to check. I'm sure he's right. So 676 is a perfect square. 26 is its square root. Does anyone have any questions so far about the concept of a perfect square or a square root? Chris? Okay, so now we're going to shift gears but use the same idea. So everyone draw another square. Now I'm going to choose the next one. Let's find out if x squared is a perfect square. If it's a perfect square, that means I can find something that it can multiply by itself to get the number or the expression inside. So what is there something that I can multiply by itself to get the x squared? Davis?
X.
Let's see if that works. X and x times x, does that equal x squared? It does? Yeah, it does. Absolutely. So that seems logical, and I think most of us knew that. But now here's the hard part. Let's see who can come up with it. I would like a different example of an expression that is a perfect square. So it's going to be just like mine, but a little bit different. Nathaniel?
225 x squared.
I don't want any numbers. I just want a variable.
X to the 16th.
Okay, let's try it out. X to the 16th power. Is that a perfect square? Okay, so here's the hard part. What goes on the outside of the square? X total? Well, let's find out. Write this down lightly, ladies and gentlemen, because we're not sure about this yet. Is that correct? Chris? It's not correct. Kadir, what did you think? Thought it was x to the 8th power. So, could someone explain? Because Kadir and Chris are correct, and it's actually x to the 8th power and x to the 8th power. Now, Kadir was totally innocent. He didn't do anything wrong. Because he's saying to himself, well, wait a minute, 4 times 4 is 16. So what's going on here, Dalton? But why? Why do we add them this time when clearly before we were multiplying? 4 times 4 is 16, 2 times 2 is 4, 26 times 26 is 676. So I'm supposed to multiply this. X times x is x squared. X to the 8th times x to the 8th is x to the 16th? Didn't You're in the ballpark. You're in the right ballpark, in the right area, with the wrong name. John?
Well, having an integer is just another way of saying this number times itself by this time to make it shorter. So it's the same thing as x times x. So then it would make sense to add them instead because, like, if you were to multiply x times 8 and then you're supposed to add them.
That's right. And so you got the right idea, but your explanation was just missing a couple of things, Michaela. Well, that's my favorite property, but that's what Janae said. That's not the same one that we're looking for. Power of a power is when you have x to the 3rd to the 4th power. That's power of a power. That's not what's going on here, but as I said to Janae, she's in the ballpark. In fact, she's very close to what we're talking about. So the question is, which one are we talking about? I'll give you a hint. It's on the bulletin board over there. Danielle? This is called the product of powers. And you learned in chapter 8 that when you multiply powers together, you add the exponents. So this is a big point of confusion for students. That when you multiply powers, you are multiplying, yes, we are multiplying this whole expression times that whole expression. That is what we're doing. But when you do that, you add the exponents together to get the result. It's just not the same thing. It's still multiplication, but it doesn't work the same way. That's all. You have to be keenly aware of what's going on here. So let's see if we're starting to catch on. Can someone give me another example of a perfect square with a variable? Zumar? X to the fourth. Let's see if she's right. X to the fourth, what would go outside the square? X-dol? Very good. X-dol is catching on. X to the second times x to the second will get you x to the fourth, because when you multiply powers, you add the exponents. Give me another one. Give me another one. Only 3 people can pick one for me? My quiet students, stay on your toes. You're starting to get involved, starting right now. Stephanie. X to the 10th. What goes on the outside? This is an important one. You picked a really good one. What goes on the outside? Alexandra, what do you think? X to the 5th. X to the 5th. Very good. Give me another one. Bump. Look at what's up here now. Think about it. X to the 30th. Let's test it out. What goes on the outside of the square to make that work? Andrew? X to the 15th. Give me one more. Michaela? X to the 12th power. What goes on the outside of the square to make it work? Dalton? X to the 6th. Wait, don't say it. So I have 6 different examples up on the board. Does anyone notice anything about all the perfect squares that have variables in them? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people notice something. Dalton will start us off, and let's see if everyone was thinking the same thing. Okay. So the exponent on the outside is half of the exponent on the inside. Good. Is that what you were thinking? Okay, what were you thinking? Say it again. What's all even? Yeah, the exponents are all even. That's a 2, that's a 16, that's a 4, that's a 12, that's a 30, that's a 10. For a variable expression with a power to be a perfect square, the power must be an even number. That's important. Anyone have any comments or questions about what we did here? Because now the building process isn't even done. Yes?
If it was x to the third power, would it be x times 1.5 and x to the 1.5 power?
Well, unfortunately, x to the 1.5 power is actually not what you think it is. Fractional powers are not what you think they are. It means something totally different that you would never imagine, and you will be introduced to it in Algebra 2. So now, from this idea, we get a bunch of radical concepts. So now, we're going to go one at a time, but we are going to go pretty quickly. Actually, let me do this way. So here are some ideas to consider, radical rules. Okay? Things that you have to know instinctively in your brain to work through the questions we're going to be doing. Now I'm going to shift this and start over here. So first one we already know. The square root of x squared is x. We just figured that out by looking at those squares on the previous page. The second one also was clear on the other page. The square root of x to the 4th is x squared. So I can re-illustrate that right here. The square root is what's on the outside. The square root of x squared is x. The square root of x to the 4th is x squared. Okay? But This is one that you're going to start learning right now that it makes perfect sense. Radical x times radical x equals x. And the reason that this works is because when you multiply a radical times a radical, what you actually do is this. And x times x is x squared. And what's the square root of x squared? It's x. And so what we get from this is that anytime you multiply a radical times itself, the expression inside the radical jumps out. This is an important trick to know. I've also illustrated it with numbers here. Radical 2 times radical 2 equals 2. Why does that work? Because of this. You multiply them together, you get radical 4, and what's the square root of 4? 2. So you don't have to do this, you just have to know that a radical times itself equals 2. Here's the other piece. When you have a multiplication problem inside the radical, you are allowed to split it into a multiplication problem of the first factor times the second factor. That's a factor, and so is that. So you can split it so that it looks like this. This is important. This is what allows us to simplify things. Same thing is true for a fraction. If you have radical of a fraction, you can rewrite it as the square root of the top over the square root of the bottom. This allows us to simplify one part at a time. So we are going to use all of these ideas to simplify expressions. That was the building process. Now we have to learn how to use it all, how to apply it. So do not go ahead of me. Stick with me. I'm going to be working at a pretty moderate pace. So the first one we're going to simplify is radical 45s to the third. Today I'm going to be modeling thought process. So I'm going to be speaking and I'm telling you what's going on in my mind as I'm trying to simplify this. Okay? So here's the thought process. Okay, 45s to the third. What perfect squares are there in that? So start out by splitting things. So I'm going to rewrite this as radical 45 times radical s to the third. So now I can concentrate on the number and I can concentrate on the variables after. And now I'm looking at the 45 and I'm saying to myself, okay, what numbers multiply to 45 and I want one, hopefully, or two of them that are perfect squares. Okay, I got it. Anyone else got it? You don't have it? Only two people can figure out two numbers that multiply to 45? Seriously? Good to hear? 9 times 5. So now I can split this into radical 9 times radical 5. That's good because of the radical 9. Now, this. Well, this is actually easy, and it's going to take you a little time to get used to it. But there's a perfect square in here. What is the perfect square inside the s to the third? Chris? S squared. So s squared is a perfect square times, and what's left over? Just one s. So what I've done is I've taken this and split it into factors and then split these into factors. And I did this, we did this, so that we had these. Right here. That and that. Now take the square root of anything that you can take the square root of. The square root of 9 is 3. It's not radical 3. The square root of 9 is 3. The radical symbol disappears when you use it. Radical 5 cannot be done. Without a calculator, we're going to leave it. The square root of s squared is s. We just learned that when we were looking at those squares. And the square root of s can't be done, so we leave it. Now, anything outside the radical goes to the front and gets put together. Anything inside the radical gets put together in one radical at the back. So this and this is going to come to the front right here. And then this and this are going to come to the back right here. So the 3 and the s becomes 3s, and then the radical 5 and the radical s becomes radical 5s. There are no more perfect squares for me to find in here, so we are done. That is simplified. Now, if it still doesn't make sense, good. It shouldn't. You've seen one question. Are there any comments about what was done? Good. Let's keep going. Part B. Radical 124, m to the 4th, n to the 10th. So again, I want to do the same thing I did over here. Now, as I get better and better at this, I'm going to start eliminating steps because there's lots that you can do mentally. Some of you guys might be there already, but I don't think most of us are. So I'm going to separate each of these into factors. So, radical 124 times radical m to the 4th times radical n to the 10th. Now, anything that can be split into perfect square into factors, we want to do. The number is usually the one that's going to take the longest. So I need 2 factors of 124. Okay? 31 and 4. Is there a bigger perfect square factor? Like, is it divisible by 9? Is it divisible by 16? Is it divisible by 25? Yes. Okay, 62 is a bigger factor, but it's not a perfect square. 2 is not a perfect square either, but you're right. 62 times 2 will equal 124. But we want a perfect square factor, so this is the only pair that helps. This is already a perfect square. Remember the observation that was made by Alexandra, that all of the perfect squares had even number exponents. If you have a variable with an even number exponent, it is by definition a perfect square. So this we want. We don't need to do anything with that. This we want. We don't need to do anything with that. Now, take square roots of things that you can take square root of. Square root of 4 is 2. Square root of 39 cannot be done without a calculator, so we leave it. I'm sorry? I thought I said 31. Okay, 31, sorry. What is the square root of m to the 4th? Let's see who was paying attention 10 minutes ago. Square root of m to the 4th. Davis?
M squared.
That's right. M squared. I think that was an easy one. Let's see who was really paying attention. What's the square root of n to the 10th? Sebastian? Very good. N to the 5th power. Nice. And now, just as I said before, anything outside the radical is going to jump to the front of the line. 2 is going to jump to the front. M squared. N to the 5th is going to jump to the front. Anything inside the radical goes to the back of the line. So, here's what we end up with. 2 m squared n to the 5th radical 31. And that is simplified. Does anyone have any comments, questions, concerns? Dalton.
What if you don't pick the highest common factor?
Here's a problem. You can do it, but then you're going to have to do it again. Okay? trying to think of an example. 48. Number 48 is divisible by 4. So that's a perfect square. So you could split it into 4 and 12. So then you could take the square root of the 4. But what's the problem with the 12? Chris? This can be split up into 4 times 3, and the rules are that you're not allowed to have any perfect square factors, which means you would have to split it again. Does anyone know what the biggest perfect square factor of 48 is? Extol? 6 is not a perfect square, and 8 is not a perfect square. One more factor. Danielle? 16 and 3. If you split this into 16 and 3, the first shot so if you do 16 and 3, then you take the square root of this, it's 4, and then you leave that as radical 3, and then you're done. Okay, so you can do it both ways, but one's going to go faster than the other. Okay? Good. Good question. All right, so as I said, we got a lot to cover today. It's definitely not easy. It's a long process. We got 2 more we're going to do, and then you're going to be on your own for a checkpoint. So we're going to go a little bit faster. So we're going to start out by splitting everything up. And in fact, you can think of this as something that's already been split up a little bit for us. It's a multiplication problem, but we're really trying to split things to simplify them. So we rewrite this as radical 27 times radical x times radical y times radical 5 times radical y squared. Each factor was separated into its own radical. Anything that can be separated any further? Anyone see anything that can be separated further? John? Yeah, split it to what? Very good. So this can be split into radical 9 times radical 3, and then the rest, we'll just leave it alone. So all of this is just going to come right down there. Now, any perfect squares will get taken care of. So here's a perfect square, and here's a perfect square. Take the square root. This is a 3. This is a y. The rest, nothing can be done. So leave it inside the radical. 3, radical x, radical y, radical 5. Anything outside the radical jumps to the front of the line. Anything inside the radical gets pushed back together inside one radical. So the 3 and the y comes to the front of the line. And then we're going to make one radical for the back of the line. And now you have to multiply numbers that are inside the radical. Radical 3 and radical 5 is radical 15. And then we have an x and a y. And that is it. We have simplified the expression. Any comments, questions, concerns? Lastly, a division. I did illustrate briefly that when you have a division problem, all inside the radical, that you can separate it into radical of the top over radical of the bottom. So this can be rewritten as radical 121 over radical 16x squared. My really advanced students are pretty much done already. Anyone know what the answer is going to be? 4 people. Matthew, you don't know what it's going to be already? What's the top going to be? Very good. So the top is a perfect square, so that will be 11. What about the bottom? Very good. Square root of 16 is 4. Square root of x squared is x. So the square root of 16x squared is 4x. Boom, we're done. Nicely done. Any comments, questions, concerns? The semi-good news about these is that it's very puzzle-like, and there's more than one way to simplify. And so it's up to you to kind of figure out what's the most efficient and meaningful way for you to do it. Okay? So now, I'm going to put up the first checkpoint. I decided to do something a little bit different, and the first check... Oh, no, I'm sorry. No. Yeah, the first checkpoint is 2 questions. I wanted to give you a chance to really explore some different types. And both of these can be done in multiple ways. So it's up to you to try and figure out what can be done. So 2 questions, you got 4 minutes. That's a bit longer than my usual checkpoint. let's see how we did on our own. Sorry. Okay, I apologize. So, what'd you get? Let's see how we did, and let me just up front say that if you didn't get it right, it's not time to get discouraged. You've seen only 4 questions, okay? So, let's see what we got. Davis, Nathaniel, Kadir, Alexander.
For the first one I got
Just part A.
10c squared times the square root of 45c.
Okay?
3c squared times the radical of 50c.
Okay?
15 c squared times radical of 2c.
Okay?
3c squared times radical of 50c.
Okay? So we have 2 people who agree here and here, but we have disagreements here and here. Dalton for the same one, and then Stephanie.
15c radical 2c.
Okay?
15c squared to the radical of 2c.
Okay. It is 15c squared radical 2c. Part B, what'd you get? We'll start with Janae, and then we'll go to Ziamara, Kalasia, and then Daniela.
J squared times
Okay? I think that's what she said. Okay. Wow, all 4 of you agree? The correct answer is a squared b. So now, let me back up. And Nathaniel, can you tell me what your answer was again? For A.
3c squared times the radical of 50c.
So could someone explain why his is wrong? Because he did a good job. But why is it wrong? Ziamara? Yeah, there's a perfect square factor still inside the radical. There's a perfect square factor right there. Those are 25. So you have to get rid of that perfect square. So you could actually go from right here and finish. You could take this and split it into radical 25 times radical 2c. The 3c squared is here. Now this will get taken out. Square root of 25 is 5. 5 times 3 is 15. C squared radical 2c. This was an issue of not picking the biggest perfect square factor. Does anyone know what the biggest perfect square factor of 450 is? Matthew? 225. So let me back up again. Here's how you would rewrite it. Square root of 225 times square root of 2 times the square root, and now what's the perfect square in there? The biggest perfect square. Kadir? C to the 4th times radical c. It's very simple to turn this into the multiplication of 2 factors. The biggest one will always be 1 less. Do you see that? All we do is take the 5, reduce it to a 4, and then we have 1 left over. So now we have perfect squares. The square root of that is 15. The square root of that is c squared. This stays, and this stays. Perfect. Whatever's outside the radical goes to the front. Whatever's inside the radical comes out to the back. 15c squared, radical 2c. Comments, questions about part A? Any other comments, questions? Good, let's take it to the next level. So we're going to proceed the same exact way, not doing anything different. We have a division problem, so we want to immediately change it to this over this, so we can simplify things separately. And now we want to take care of any perfect squares. So let's look at the top first. Are there any perfect squares in there? Any perfect squares? Give me a thumbs up if you think there's a perfect square in there. Nobody thinks there's a perfect square. So we're not catching on yet. Because there is. There's a perfect square in there. What is the perfect square in there, Alexandra? No, I just want to know what is the perfect square inside the numerator. Well, x to the 5th power is not a perfect square, but there's a perfect square in there. What is it? Very good, x to the 4th. And so this can be rewritten as radical 7 times radical x to the 4th times radical x over radical 11. Now we have the perfect square, and we can take the square root of it. There are no other perfect squares. Now I'm going to continue up here. So I'm going to continue right over here. So we're going to take the square root of this out, and it's x squared. The rest will get put back in. Radical 7x over radical 11. So we're done. There are no other perfect squares. But now there's a problem. One of the criteria, one of the conditions for me to be done with my job is that there cannot be a radical in the denominator. So you are not allowed to have this. So we are going to use the technique called rationalizing the denominator. And it's very simple. Once you're done simplifying everything else, which we are, you multiply the top and the bottom of the fraction by whatever's in the denominator. So we're going to multiply the top and the bottom by radical 11. And I'm going to continue going down. So now multiply everything out. X squared is outside the radical, so that's going to stay outside. Radical times radical, you multiply what's inside times what's inside. We have 11 times 7, 77x. Excuse me. Here's the magic of rationalizing the denominator. Radical 11 times radical 11 equals 11. And so we have rationalized the denominator, and we have done our job. We have simplified this as far as we can. Anyone have any comments or questions on how we did that? Comments, questions? All right, let's see it again. Square root of 125 over 4x to the 3rd. Your brain should be getting in tune with... Should be getting in tune with where the perfect squares are. So, radical 125 over radical 4x to the 3rd. But now let's find some perfect squares. Any perfect squares on the top? We got some light bulbs going off. Ziamar? Yeah, 25 times what? Good. I'm going to work to the right. Radical 25 times radical 5. What about the bottom? What are the perfect squares on the bottom, if there are any? Hayes?
Radical 4.
Good.
And radical x and radical x squared.
Very good. Yeah, you reduce this by 1, and that's a perfect square. And then we have 1 left over. Beautifully done. Now, all the perfect squares jump out of the radical. There's a perfect square, there's a perfect square, and there's a perfect square. They jump out. They're going to jump out of the radical, jump out, jump out. Square root of 25 is 5. This is still left over, so we have radical 5. Square root of 4 is 2. The square root of x squared is x, but then we have this left over. We have simplified everything we can simplify, but unfortunately we are left with this down here. We're not allowed to have that. So what do we do? One person who knows? 2 people? 3 people? 4 people? Dalton? Very good. We're going to multiply the top and the bottom by radical x. Work this way. 5 is going to stay. Radical 5 and radical x will be radical 5x. Now I'm going to have a radical x times a radical x. What will that turn into? I'm just looking at this and this. What will that turn into? Edgar? X. But I already have an x here on the bottom, so I'm multiplying this times the result of this. So what will the bottom turn into, Kadir?
2x squared.
Very good. Since this turns into an x, we're multiplying it by x, we get x squared. And now it is simplified. Okay? That is rationalizing the denominator. That is definitely not easy, but you've seen 2 examples. Does anyone have any questions? All right, I had another example, but I'm going to skip over it. Let's see how you do on your own. Checkpoint number 2, got 2 questions. Got 3 minutes. see how we're doing with simplifying expressions when you need to rationalize the denominator. What do we get for part A? We'll start with Danielle, Stephanie, and then we'll go to Chris.
There's 5x over 5x.
Okay.
Radical 5x over 5x.
Is that what you said, Danielle?
Yeah.
Okay, Chris? Okay. So radical 5x over 5x is correct. Nicely done. What about part B? We'll start with John, and then we'll go to extol, and then we'll go to funk.
A times the square root of b over 2b.
Okay?
Times the root of b over 2.
So you got the same thing. Good. Funk. Okay? The correct answer is square root of b over b.
Cancel out.
How did I
So,
see that?
the good news is that you guys did everything right. The bad news is you've got basics from a long time ago, which is that when you have an A on the top and the A on the bottom, you cancel them out. So there's good news, bad news. I'm proud of you. I'm very impressed. I walked around and a lot of people were pretty much close. But let me show you one other thing that you can do, and this is where I was talking about these being like puzzles. So now I want you to look at the answer, and now look at the original question again. Anyone notice anything now? You see something now? Nathaniel, what do you see now?
It's just that. Well, it's just it's root b over b, but the top has to be a square root of the radical sign.
Right, okay, but how does that relate to the original question? It's not really flipped. So what can you, look at the original question now that you see the answer, Extol.
Cross out the a on top of it.
Yeah! Right at the beginning, you can cross out the A, and this becomes radical 1 over b. So, that you didn't have to do that, but I'm just proposing the idea that there might be a simpler way to do things if you just pause and think about it for a moment. Okay, so you guys are doing an awesome job, and I know that it's been difficult, it's been a long road, and unfortunately the road is not over. But it's close, but it does get difficult. And I did say at the beginning that we were going to be pulling ideas from all over the place. And here is where we're going to take the ideas you learned today and pair them up with ideas you learned in the past. Your brain's going to start to melt. Your brain's going to start to get a little fuzzy because it's hard. Okay? But I promise you that just take your time, stick with me, you will have an understanding. So, example 3. Let me get rid of this for a moment. So, now we're going to learn how to simplify expressions that have addition in them as well. So far all we've done today is multiplication. And before we get to A, I want to refresh your memory about something you learned a long time ago. So do not copy this down, I just want you to look. Do not copy that down, just look. Can someone tell me what that simplifies? I should see every single hand in the room up. And since I actually do see every hand up, I'm just going to call on one of those hands. Kalasia? Say it a little louder. How'd you do that? Added what? I'm sorry? Good, great phrase, like terms. Specifically, what part did she add? Could someone use some more math terminology? Well, that's what she said, the like terms. But what part of the like terms did she add? There's a big fancy word that you're supposed to know. Funk? Yes, integers, but specifically, what are they called in algebra? The coefficients. So now, what do you think? What do you think you could do if it was this? What do you think you could do there? Caleb? Yeah, it actually works the same way. So this would be 13x. This is 13 radical 3. If you have the same radical, then you can add them together. Just like if you have the same letter, you can add them together. So now let me show you an alternate. What if it was 2x plus 3x plus 8z? What would that come out to? Edgar? That's right. You can't add the 8z with the others because it's a different letter. So now let me extend the idea. 2 radical 3 plus 3 radical 3 plus 8 radical 5. What would the end result be there? Stephanie? That's right. You can add the ones that have the same radical. So now we're going to apply this concept that you already knew to this expression in part A. So, do we have any radicals that are the same? Zumar? We do? What are they? Okay, so you're talking about this? Okay, so I could split this into radical 5 times radical 3, and then I have the same radical, but then how do I add this and this? We don't know how to add that. You'll learn that in like 3 years from now. So you got the right instinct, but that one doesn't help us. There's someplace else we can do something. There's a perfect square somewhere in here. Where's the perfect square? That's what your brain's supposed to be looking for, perfect squares. Danielle? Yeah, what's the perfect square? Good. So if we just focus right here, let's forget about the rest. This is really negative 2 times radical 9 times radical 3. But radical 9 is really a 3. That's a perfect square. So it's going to jump out of the radical. And so we end up with 3 times negative 2 is negative 6 times radical 3. Now bring down the rest. We have the radical 15 from here. And we have this we haven't used, plus 5 radical 3 minus 6 radical 3. Now we have some like terms. So we have positive 5 radical 3 and negative 6 radical 3. Those can now be added together just like we demonstrated a moment ago. The radical 15 can't be used just like we demonstrated a moment ago. So the radical 15 will just stay like it is. And now we have positive 5 and negative 6. What do we get as a result of that? Those 3 people can add 5 and negative 6? Or we're so tired that we can't function anymore? Chris? I'm sorry? Negative 1. So we end up with radical 15 minus radical 3. These are not like terms, so you cannot do anything with them. Does anyone have any questions about that? As I said, you guys are doing a good job. Stick with me. What about part B? What is that an illustration of? What is that an illustration of? Just 2 people in my class of experts knows? 3 people? Caleb? That is distributive property. And so, we multiply what's on the outside. I didn't do that very well. Let's try that again. On the outside times what's on the inside. But now we've got radicals involved, and so now you just need to be careful. Multiply the first one, we end up with 3 radical 7. But the second one, we have a -2, and now we're multiplying a radical 7 times itself. What happens when we multiply a radical times itself? We got a bunch of people who know, right? So in this case, it will turn into a, very good, times 7. And so, 3 radical 7, nothing can be done, minus 14, and there's nothing else that can be done. Comments, questions, concerns? Last one and the biggest one. What is this an example of? Let's see who remembers what this is an example of. The things?
Foil.
Yep. It's a binomial times a binomial. So remember, FOIL, F stands for the first terms. So we're going to multiply this times this. 8 radical 3 times 1. That's the first terms. The O stands for the outer. So we add, this is the F. Now we're going to add the O's. The outer is this times this. We have an 8 times a -1. So that's -8. And a radical 3 times a radical 3, Edgar, turns into a 3. So we have that plus the inner. 2 times 1, no big deal, plus the L's. The last terms, 2 times -1 radical 3. 2 times -1 radical 3. 2 times -1 is -2 and the radical 3. Now simplify anything. This has a radical 3, and this has a radical 3. They are like terms. We can add them together. We have 8 radical 3 and -2 radical 3. We get 6 radical 3. This is going to be a -24. That's a +2 minus 22. And we just did FOIL with radical expressions. Any comments, questions on foiling the binomials or distributive property or like terms? Ideas pulled from all different areas from this year. Any comments, questions? Good. So, due to time, there will not be classwork. Everyone will get a free point. That's my fault, not yours. Everyone draw a line across your paper. Your homework is page 747. We're going to do numbers 14 through 48 even, and number 68 and 70 parts A and C only. Read the next section. You must read the next section. That is not optional. There will be a quiz or a test, but with the FCAT schedule next week, I'm not sure when it will be. So I have to wait and see another